Okay, so today's topic is properties of compounds. Now that we know how to name them, hopefully, and we're getting more and more fluent at that, we need to know what are we talking about? What should I be expecting to look for? Right? If I were to do a lab, which I want to do as soon as we can in our first unit, if I talk to you about sodium chloride, what should I expect? A gas, a solid, a liquid? Should it be white or blue? Should it be soluble or not? So today is a very, very short lesson, but I just want to go over some generic properties of things. So the first thing you need to know is that anything that's ionic typically has these properties. So first thing is they usually have a high melting point. That means that it takes a lot of energy to cause the physical bonds to separate. Okay. Let's talk about why. Ionic compounds, what are they made up of? Well, it even says here, right? They're made up of alternating positive and negative charges. Those of you guys who took physics with me, think of the electrostatics unit. If you're going to have a positive sodium and a negative chlorine, we know that positives and negatives attract, right? Right? Well, that actually gives them a very, very solid, rigid structure. And these two pieces right here, they really want to be stuck next to each other, right? Doesn't that make intuitive sense? Right? Well, if they want to be stuck next to each other, what phase of matter is most likely? Solid. Right? Do gases want to be stuck next to each other? No. Here, I'm hitting some gas molecules away, right? They have no need to be stuck with each other, right? But solids, they must have some sort of like internal bond that's keeping them stuck together so that I can't phase my hand through unless I'm like a mutant or something, right? But unless I'm a mutant, right? I mean, these things are so stuck together. But here's the cool thing. It's not just this sodium and this chlorine that attract to each other. This one attaches to this one, and it also is going to be attracted to that one and to this one. I mean, imagine basically like a marble kid or something like that. This guy right here is going to be attracted to this one on its left, and this one in front of it, and this one on its right, and this one behind it. And there's not even one listed there, but there'd also be one on top of it, and there'd also be one below it. Can you guys kind of see that concept here? And due to this alternating positive and negative structure, these two properties make a lot of sense. Not only will they have a high melting point because they're probably a solid, but they're also going to keep their crystal shape. Because if you were to break this in half and somehow cleave it in half, well, these guys over here still want to be stuck together. And these guys right here still want to be stuck together. You just found a way to kind of like break it down the middle. You know what I'm saying here? If I were to like break it down the middle, would it cause these two things right here to stop attracting each other? No, they'd still be attracted to each other, right? So, I mean, I don't know, it'd be the same way as if I took a bandsaw to the chair. Would I all of a sudden expect that I slice it in half, that all the molecules just like crumble into dust? Well, no. I mean, there's still structural integrity on both sides. I cleaved it in half. So, anyways, two very hopefully logical properties. Very, very strong crystal shapes and a high melting point. Another property we need to consider is not so much a physical property, but a chemical property. The property of, well, what happens if you put it into water? Who has seen this chart before? Okay, some of you seem to recognize it. This is a chart that helps you tell whether or not a compound is going to be soluble in water or not. And it's found in your data booklet here on page 6. Page 6. It looks like this. Okay, first thing I should make sure I'm clear on, do you guys know what soluble means? What's a synonym for soluble? Yeah, that's what I was looking for. Yeah, it dissolves, right? If something can dissolve and be pulled apart, then it's soluble. And let's go back and talk about why things dissolve. Okay, ionic things are made up of positive and negative charges. Okay, water is actually considered to be a polar molecule. If you haven't heard that word before, it's highly polar, which means it actually has a negative end to it and a positive end to it. And it actually has the ability to attract these negatives and these positives and actually dissolve them, pull them out of that solid crystal shape, and make it so that they, almost like a magic trick, they disappear. Who's ever made Kool-Aid before? You start with solid crystals, you stir them up in the water, and all of a sudden the solid is gone. I mean, I know the Kool-Aid just turned purple, but the solid is gone, minus a little bit of sugar at the bottom, maybe. You get what I'm saying here? That's dissolving. many things dissolve, like salt would be another good example. Put salt in water, and the solid is now missing. Well, it's not missing, it's just the water molecules actually pulled this guy and this guy and this guy and this guy apart, because water is actually more polar than the substance itself might be. Now, here's basically a table then that will tell you whether or not the substance will dissolve or whether it won't. The top column right here, the very soluble column, you might even want to write this down here. These things dissolve. Okay. If something fits into the top column, it will indeed dissolve. And sometimes we give the state of matter. We use AQ. AQ stands for aqueous. Yeah, basically it means that it's now no longer in a solid, liquid, or gas form, but it's now been dissolved in typically water is what we dissolve things in. If something is slightly soluble, then really it did not dissolve. Or at least you might say it did not dissolve well. Like some of it might have dissolved, but there's a lot of precipitate left over, if you've heard me use that word precipitate before. I'll make sure I show you guys this in a lab setting one day. But if you've ever seen a cloudy looking beaker where there's some solid crap kind of left inside, if you know what I'm talking about here, that's something that's slightly soluble. So we would use the state of matter solid because there's still some stuff in a solid form that did not manage to dissolve. So then the question is, how the heck do you use the table? So essentially what you want to do is if I give you a substance, like say sodium chloride, you want to start by focusing usually on the anion because the top row right here is mostly anions. So you got to find where that anion is along the top row, and in sodium chloride's case, the chlorine part is right there. Make sense so far? So if I want to figure out whether sodium chloride will dissolve in water, since here's the chlorine, now I look down the column. And it usually works like this. One of the columns is the word most, and in the other column is the exceptions. So like down here, silver with chlorine would not dissolve. Lead with chlorine would not dissolve. Mercury, all these guys right here, they would not dissolve with chlorine. Which column is sodium in? Well, sodium is not one of these five, so sodium would be in this table right here. So chlorine with sodium would dissolve, which is why it makes sense. When you put salt in water, it will dissolve. Let's try a few more examples here. What if I gave you calcium carbonate? Would you expect it to be an aqueous solution, or would there be a precipitate left over? Okay, so to do this, find your carbonate. Your carbonate ion is right here. Well, if it's in group 1 or it's an ammonium, it'll dissolve. Is calcium in group 1? It's in group 2. So that means it's in the bottom category because calcium is in here with literally everything else on the periodic table minus these exceptions. So then you'd expect the calcium carbonate to be solid. Last week I said something which I immediately regretted because I didn't want to say it, but my general rule is I want a state of matter always. And I think at the time I said, and if you don't know, guess. And then I was like, wait, that goes against what I always tell you guys to do. Now, though, you shouldn't need to guess. If you're trying to figure out a state of matter, this chart should help you able to figure out whether it's solid or aqueous. Does that make sense? It's just at the time I hadn't shown you this chart. Do you guys, who's seen this before and feels like they get the idea? Okay. Why don't I do just two or three more examples just to make sure we're clear, and then we'll move on here. So why don't I give you guys these ones here? Tell me what you'd expect a copper chloride to be, what you'd expect a sodium hydroxide to be, and let's try a magnesium bromide. See whether you think these things would be solid or aqueous. All right, so for the first one, find the anion chlorine. Chlorine is with bromine and iodide in a table, and there are 5 exceptions. Otherwise, everything's soluble. But believe it or not, copper 1 is actually one of the exceptions. You see how Cu plus is literally the first thing on that list, right here. Copper is on the list of exceptions, so this one we'd expect to be solid. So will copper chloride dissolve in water? Not really. Okay, sodium hydroxide. Find the hydroxide, which is in this column right here. Almost everything is in the not dissolving column, except for a few exceptions. Thallium, barium, strontium, and ammonium, and anything in group 1. Where's sodium found? Okay, so it's aqueous then, because it is in the top column. So sodium hydroxide actually should dissolve. That makes sense? And then for the last one, magnesium bromide, we need to find the bromine column, which is actually the same thing as the chlorine column. Bromine is not one of my 5 exceptions, which must put it in the top in most, which means it does dissolve. So I would expect magnesium bromide to dissolve in water. Do you have any questions on that? Okay, cool. Okay, another thing we should talk about then is conductivity, another physical property. If something is ionic, here's a kind of a visual of what occurs. Ionic compounds are made of interlocking positive and negatives. And from electrostatics, positive and negatives, we do know, really like to be attracted to each other. So they have a high boiling point and they have a firm, rigid shape. But water is polar, and water is able to pull these ions apart. Now, once these ions are pulled apart, you have negative and positive ions just kind of sitting there in solution. Well, that can actually conduct electricity. Because what's electricity? The flow of electrons. Yeah, electrons can flow through a positively, negatively, bipolar kind of solution because of the way that electrons move. So if you've got negatives and positives separated, they actually should conduct. So pretty much anything ionic has the ability to conduct. The more that it dissolves, probably the better it conducts. Okay. This is actually one of the reasons why water and electricity don't mix. You guys have ever heard, like, don't drop the toaster in the bathtub because you'll electrocute yourself? Wow. It's a good question. Okay. Water on its own, pure 100% no dissolved ions water, actually doesn't conduct electricity. I'll prove that to you guys a little bit later if you want. I'll grab some what do we call it again? Distilled water, that's the word. If you were to take distilled water and try to run a current through it, it won't conduct electricity. However, I'll use Joe's water bottle as an example there. That's probably not distilled water though, right? On the side, it probably has like all sorts of dissolved ions, like a little bit of magnesium, a little bit of chlorine, right? Like a couple parts per million. Those are what conduct electricity. And so unless like the ocean or the bathtub or whatever you're talking about, unless you're bathing in purely distilled water, then water actually conducts electricity very well. So that's why usually you want to say electricity and water don't mix. That's actually true unless it's pure water. If it's pure water, it actually doesn't conduct at all. So, does that make sense? Okay, the opposite or other side of the coin to ionic compounds are molecular compounds. So these guys are ones that share electrons. They actually have almost complete reverse properties. They have a low melting point. The reason why is that these guys are not having positives and negatives being interlocked, but they're their own unique structures. And so there is a little bit of attraction, but they don't tend to bond very well with other ones. Almost everything that's covalently bonded, you guys will probably even recognize as not being solid. Like, for example, carbon dioxide is covalently bonded. Right? You've got your carbon, your oxygen, they're both nonmetals. This guy right here is a gas, because there's really not a lot of reason for this carbon dioxide over here and this carbon dioxide to be attracted to each other. Like, there's not a lot of reason for them to attach to each other. But there's a lot of reason for a positive and a negative and a positive to attract to each other. But these guys right here, the way they bond, they don't actually bond that same way. Even water. Water is kind of molecularly bonded because the hydrogen and oxygen share. But At room temperature, water is probably a liquid at best, right? The only way you'd actually make it a solid is to drop the temperature down really low. So most of these guys right here have a low melting point, and because of that, they're usually gases or liquids. So ionic things are usually solids. Molecular things are usually gases or liquids. And because of that, even if they form crystals, which many really don't unless it's like minus 200 out, the crystals they make are very weak. Like think water. Can water form crystals? Yeah, we call that frost. But I can get rid of frost on my windshield by just literally scraping it off with a scraper. That's not all that hard. You get what I'm saying here? So the crystals to covalent compounds are not that strong, but imagine that I were to coat the surface of your window with like aluminum chloride, and then you had to scrape that off in the morning. I don't know. That probably is going to be a little bit stronger than just the frost, right? Frost flakes off, no problem. But something that's like a solid residue that's maybe an ionic compound, it's got more strength to it. So. Okay. Well, if ionic things have the ability to break up into positive and negative anions and cations, and those things are what allow the flow of electricity to happen, well, covalent things, if they don't break up into positives and negatives, usually they're not electrolytes. So you would expect covalent things to not conduct electricity. Just like a minute ago, I mentioned water. Water is a covalently bonded molecule. The hydrogens and the oxygens share the electrons. So pure water on its own actually doesn't conduct electricity. But dissolve some ions in it, like almost all water has, then it will conduct. So does that make sense here? Molecular substances don't have the positive and negative components to it. Here's kind of a picture to illustrate what I'd be talking about. I want to do this in a lab in a week or so when we get to our new curriculum here. But the basic idea would be if you were to have a solution and try to run a current through it without having these two electrodes touch each other, this guy right here, CH3OH. You remember what CH3OH is? Methanol, yeah. Methanol is covalently bonded because carbon, hydrogen, oxygen, hydrogen, all of these are nonmetals. These guys all share electrons. They should not let the light bulb light up. However, sodium chloride, NaCl, totally breaks up into positives and negatives, and the exact same setup here actually will let the light bulb light up because the current actually has a medium through which to pass. It is possible to have some things that are kind of like in between where they're like iffy, where it lights up a little bit, but right now I'd rather leave the exceptions aside. So general rule of thumb, ionic conducts, molecular doesn't. That more or less fits everything. So, any questions? Okay. Other properties we should talk about involve the pH of a solution. You guys have heard of pH before, right? Anybody know what pH stands for? Nice. Powers of hydrogen. Yeah. Powers of hydrogen, or the pH scale, basically describes the acidity of a solution. And so I've got a few slides here talking about acids and bases. Really, there's that sliding scale. You guys have heard of this before, where like 1 and 2 and 3 on the pH scale are acidic. 11, 12, 13, 14 are bases. In the middle at 7, you've got your neutral substances. So all solutions should fall somewhere into this range. So acids, here's some properties of acids. Acids actually are soluble in water to some degree. They're kind of the exceptions to the rules. They do conduct electricity. Have you guys ever seen litmus turn red? Lav ever do that? I'll make sure I show you guys this in a week as well. But they actually cause litmus to turn red, and they're usually sour. And so those are acidic. So these are things that are a pH that are going to be less than 7. So if your pH is a low pH, it's acidic. And anything that's acidic has a special acid name. And I realized in hindsight, I think I showed you guys how to name acids the other day, right? I actually had notes on these. I forgot. So I'd like to go over it just one more time if we could. Here's how you name... Let me skip ahead. Can you skip a slide? I'll come back to bases. Let's just do a quick review on how to name acids. The way you name acids is there's typically a hydrogen first, and then there is an unknown part second. And depending on what the unknown part is, there are a couple different ways that you can name that acid, depending on what this thing is. But it usually needs to involve a hydrogen first. Usually. There's exceptions to every rule. So like, for example, let's say I gave you HCl, hydrogen chloride. Okay. The way that we name this is if it was a binary thing with an H and a Cl, we called it hydro something ic acid. So if it's HCl, it's hydrochloric acid. If it's HBr, it's hydrobromic acid. If it's HF, it's hydrofluoric acid. So only if it's a binary substance do you use hydro in front and call it a hydro acid. Okay. Otherwise, everything else we're going to talk about is a polyatomic. So if this polyatomic that comes second is an 8, I gave you guys that silly rule the other day, right? You ate something icky. So if it's an 8 atomic, polyatomic, turn it into an ic. So hydrogen nitrate becomes nitric acid. Hydrogen sulfate becomes sulfuric acid. Hydrogen chromate becomes chromic acid. So 8s or ics, basically. If there's a per in front, then just keep the per in front. So if you have a perchlorate, then call it perchloric acid. So if it's binary, add a hydro in front. If it's an 8, make it an ic. And if it's an ite, make it an us. And again, my silly little rule for that is when you get into a fight, ite fight, and someone punches you in the gut, you say us, because you got hit. It's dumb, but it works. I hope. So anyways, if you have a hydrogen chlorite, it's chlorous acid. The ite turns into an us. If you have a hypochlorite, it becomes hypochlorous. So those are your special rules for naming acids. All right, let me go back. Sorry I skipped this slide. I know I'm going out of order here. The flip side to being an acid is a base. So bases are things that would have a pH that is going to be greater than 7. So if you have a pH higher than 7, 8, 9, 10, 11, 12, 13, 14, you're talking about a base. And for right now, the best way to define a base for us is that it's going to have hydroxides on it. If it involves an OH, a hydroxide anion, that's a good indicator that it's basic. Again, this is actually not a hard and fast rule because there are always exceptions. But if I gave you, like, say, CaOH2, that's a base. If I give you AlOH3, that's a base. NH3 is actually a base as well, though. This is where I'm going to have to show you some like basic rules, and we'll get to the exceptions later. But for right now, if you see an OH, it's a good indicator that it's a base. But there are other things that are basic that later I'll try to explain to you why they're basic. So, bases are bitter. They're actually also usually soluble in water. They usually conduct as well. And these guys turn litmus blue, if you've seen that before. If not, I'll show you in a week. Okay, I think my last slides are just examples. Yeah, okay. So let me recap what I wanted to talk about today. I need you guys to know some properties of things. Really, I can break it down into probably 4 main categories here. I need you to break things down into the properties of your ionics versus your moleculars. Ionics, solid, rigid structure. High melting point, high boiling point. They are highly defined. If you cleave them in half, you still get 2 halves to them. Okay. They may or may not be soluble, but those are your ionics. Your covalent things, your molecularly bonded things, they don't stick together. There's no positive and negatives to them to have them stick. So carbon dioxide would be a great example. What keeps this carbon dioxide molecule right here next to this one over here? Nothing, really. Right? There's no reason for them to. What keeps sodium and chlorine next to each other? Well, one's positives, one's negative. Positives and negatives really like to be next to each other. But covalently bonded things, that's not really the case. So covalent stuff should be liquids or gases. Okay. As well, covalent stuff doesn't usually conduct. Ionic stuff does. Okay, so those are two categories of properties you should know. The other ones are acids and bases. Okay, acids have a low pH. They usually conduct and they're usually sour, whereas bases have a high pH. They actually also usually conduct as well, but they're usually bitter. I want to add a few more properties to the list, actually. Sorry, can I go back here? Acids, the word we use to describe acids is corrosive. You guys ever heard that word before, corrosive? Acids are actually usually quite dangerous because they will corrode away. Like if you were to spill some acid on your skin or on some plastic, it might actually cause it to melt. You've probably seen a YouTube video or seen this before, right? Like acids are considered quite dangerous. Bases are actually also just as dangerous, but we use a different word to describe them. Does anybody know the word we use to describe a base? In the same way that an acid is corrosive. I've never seen that one before. Bases are considered caustic. Ever heard that word before? It's the same concept as an acid. You know how an acid will corrode and will cause you to to have like an acid burn on your skin. If you can kind of imagine that concept. Bases do the exact same thing, only we have a different name for it because it's a base rather than an acid. Okay, so both of them needed to be treated with a high degree of care because the more corrosive or the more caustic they are, the more dangerous they could be. Whereas water is neutral, it's right in the middle. Water is neither caustic nor corrosive. Does that make sense? Like water is perfectly safe to drink, but I wouldn't drink a beaker of hydrochloric acid. I also wouldn't drink a beaker of sodium hydroxide. One is on this end of the spectrum, one's on the other. You want stuff that's pH balanced in the middle. So anyways, properties of ionics and covalence, properties of acids and bases. Hopefully now you know a little bit about when you're naming stuff, you should know a little bit about what these chemicals would do. Does that make sense? So what I want to do now is give you guys the rest of class just to keep practicing. Tomorrow let's try a quiz. Okay, we'll see whether you guys have picked up on the main concepts. And then after that, the last thing we need to talk about is how to do balanced chemical equations. And that's more or less kind of our review section. So, all right, you guys have any questions for me? Things are okay so far? Okay, well, you guys have about half an hour. Do whatever it is you need to do. So I'd recommend just practice whatever you need. If you need more practice on naming stuff, do that.